Hello all, let's look at question number 45 from GATE Biotechnology 2019 paper. So the question is, a UV visible spectrophotometer has a minimum detectable absorbance of 0.02. The minimum concentration of a protein sample that can be measured reliably in this instrument with a cuvette of 1 centimeter path length is how much micrometers? And the molar extinction coefficient of the protein is 10,000 liter per mole per centimeter. So we have to solve this numerical in this question. Before that, let's have an overview about the beer-lambert law. So when a monochromatic light of initial intensity I0 passes through a solution in a transparent vessel, some of the light is absorbed so that the intensity of the transmitted light I is less than the initial intensity I0. There is some loss of light intensity from scattering by particles in the solution and reflection at the interfaces, but mainly from absorption by the solution. So the relationship between I and I0 depends on the path length of the absorbing medium L and the concentration of the absorbing solution C. So these factors are related in the laws of Lambert and Beer. This is a diagrammatic representation of what we just saw. So a monochromatic light beam of intensity I0 passes through the cuvette, which has a solution, and the length, the diameter of the cuvette is L, and the absorbing solution concentration is C, and the emergent beam is of intensity I. The Lambert's law states that when a ray of monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the length of the absorbing medium increases. So this law is given by this equation. I is equal to I0 initial intensity e power minus k1 L. The Beer's law states that when a monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the concentration of the absorbing medium increases, and it's given by the equation I is equal to I0 e power minus k2c. So these two laws are combined together in the Beer-Lambert law, which is given by I is equal to I0 e power minus k3 c and L. So transmittance is defined as the ratio of intensities of light and is usually expressed as percentage. It's generally the percentage of light that comes out of the solution other than the light that is absorbed by the solution. So the percentage transmittance is equal to I divided by I0 into 100. So because it's in percentage, which is e power minus k3 c and L. And then if logarithms are taken of the equation on both sides instead of a ratio, then log e I0 divided by I is equal to k3cl, and log 10 I0 by I is equal to k3cl divided by 2.303. So log 10 I0 by I is equal to kcl. The expression log the base 10 I0 by I is known as the extinction E or absorbance A. So the extinction is sometimes referred to as optical density. So therefore A or E is equal to kcl, where K is the molar extinction coefficient for the absorbing material at wavelength L, and C is the molar concentration of the absorbing solution, and L is the path length in the absorbing material in centimeters, and K, which is the molar extinction coefficient, is usually denoted as epsilon. So the equation for Beer-Lambert's law becomes A is equal to epsilon Cl. Now coming back to our problem statement, the relationship between absorbance A, the molar extinction coefficient epsilon or K, concentration C, and path length L in a UV visible spectrophotometer is given by the Beer-Lambert's law like we just saw. So A is equal to epsilon Cl. So to find the minimum concentration C that can be reliably measured with a minimum detectable absorbance A min, we rearrange the equation to solve for C. So C is equal to A min divided by epsilon into L. So given that the absorbance A minimum absorbance is 0.02 and the molar extinction coefficient epsilon is 10,000 liter per mole per centimeter and the path length L is 1 centimeter. So we apply these values in the equation. So C is equal to 0.02 divided by 10,000 into 1. So this gives us C is equal to 2 into 10 power minus 2 into 10 power minus 6 moles per liter. Now converting the concentration to micromolar, we multiply by 10 power 6. So C is equal to 2 micromolar. So therefore the minimum concentration of the protein sample that can be reliably measured is 2 micromolar. So that answers our given question here.